In this lecture, I'm going to talk about the interpretation and compilation, basically on the translation from the high-level language to the machine languages. The purpose of doing compilation and interpretation. Basically, we need to convert a language to another language or machine language for execution. Here, I put three typical examples: Python, that's using interpretation; C, C++, that's using compilation; and Java, that's a hybrid compilation and interpretation. Python will need an interpreter to convert the Python code into the machine code at the runtime. C, C++ would have the compiler to compile the high-level language C or C++ directly into the machine code. Java instead would be compiling the Java code into a byte code, and at the runtime, the byte code being converted to machine code again. So these three languages are three different typical languages. Pure compilation. For pure compilation, we compile a source program. It could be a C or C++ program by compiler to a target program, and then the target program will be able to run based on the input data to produce the expected output data. So the compiler translates the high-level source program into an equivalent target program. That typically is machine language and then goes away. But can compilation compile from C to Java or some intermediate code? That's possible. Pure interpretation. Interpreters stay around for the execution of the program. Interpreter is the locus of control during execution. So interpreter never go away. You have the source program that loaded in or some input script. Both of them can be run by the interpreter, and the interpreter have to be in the memory to process this program. Otherwise, the source program or the input script can never be run. Typical interpreter is a shell, for example, Windows shell or Unix shell or Linux shell. That's a very simple interpreter. And that shell translates the source program or a input script into machine code to run. Comparison. Interpretation provides greater flexibility because you can debug at runtime. Better diagnostics, providing more error messages. Compilation, because the code has been decided at the compilation time, so it will provide better performance because there is no virtual machine or any interpreter in between the source code and machine. So it is of better performance, but less flexibility. Hybrid. For hybrid model, is using a translator that translates from source program to intermediate program, or sometimes it's byte code. So this translator is also a compiler. And then when you run, you actually pick up the interpreter method having a virtual machine like Java Virtual Machine, JVM, running including the Java runtime environment and some native code, so that you can put the byte code and the runtime input together to run the Java virtual machine. For example, you can see in Blue environment, you can actually create some object other than from the program, and you can have that being tested together on top of the virtual machine. But you can look at this as one compiler and one interpreter running in combined as a hybrid technology. Common case is compilation or simple preprocessing followed by interpretation. Most modern language implementations include a mixture of both compilation and interpretation. Virtual machine. Step 1, we compile from Java to byte code. Step 2, we execute the byte code on machine with native code. Native code means some code that's been developed as a library in a platform-dependent environment. So we have Java program compiled to byte code, and then we have Java interpreter or Java virtual machine that would be machine-dependent, running on Mac OS or Windows or Linux. And that part of the library, sometimes we call it native code. So source program waits compiler to intermediate code and run on the virtual machine. That's the interpreter. Just-in-time compilation. Just-in-time compilation is a new technology at a later version of the Java virtual machine. Wait until you can no longer wait. That's the spirit of just-in-time compilation. That means you never do compilation until the code is being run. So basically you have a source code, you compile it into byte code, and then until the runtime you run another compiler to do compilation to make the execution faster instead of line-by-line interpretation using the Java virtual machine interpreter base. So the just-in-time compiler includes the following different stages: intermediate representation generator, optimization, code generation, and runtime environment. The code generation and optimizer are typical components for compilers. And Java JDK line up as JDK, JRE, and JVM. JVM including the just-in-time compiler. And JDK is the development tools. JRE are the libraries. Some important note. Note that compilation does not have to produce machine language for some sort of hardware. Compilation is translation from one language to another, with a full analysis of the meaning of the input. Compilation entails semantic understanding of what is being processed. Pre-processing does not. So pre-processing only translates symbol to symbol, but it doesn't go into the detail for semantic understanding. A preprocessor will often let errors through. Compiler hides further steps. A preprocessor doesn't. Many compiled languages have interpreted pieces. For example, format in Fortran or C. Most use virtual instructions, set operation in Pascal, string manipulation in BASICs. These are some of the derivatives to instruct the compiler or interpreter what to do. So in Pascal, it's use set operations. In BASIC, it's string manipulation. Some compilers produce nothing but virtual instructions, like Pascal P code, Java Byte Code, Microsoft Com+. And these are just intermediate codes. And Pascal is a standalone environment. It is developed based on UC San Diego P code system. These are considered some sort of virtual instruction or virtual machine. Thank you. Bye.